Assalamu alaikum. Welcome back again. So in our last video, we were here. We discussed about the S parameters, that what are the differences in terms of S parameters for the lossless power divider, resistive power divider, and the last one is the Wilkinson power divider. So let's give us a quick review. A lossless power divider is lossless, means there will be no losses in terms of dividing the powers, but there will be reflections. To solve this issue, resistive power divider is designed where there is no reflection here. Reflection at port 1, reflection at port 2, and reflection at port 3. But the power here is divided into 1/4. I mean, this is the voltage. So if we square this one, it becomes 1/4. So half of the power from the total power is lost. To resolve this issue, we have a new design which called Wilkinson power divider. In that power divider, you don't have any reflection here, and then you see the voltage here. The voltage is 1 by square root of 2. Means if you square it, it means half. So it will split the power into half. So in the T-junction, as I have already told you, in the T-junction power dividers, there are different type of structures here. This one is E-plane structure, this is H-plane, and this is microstrip T-junction power dividers. Basically, this is our goal to how we can design this one. So how the power combination and division is done is here. You can see if you input a power P1, then it will divide into if it's a 2-port output and 1-port input, means a 3-port network, 3-port device, then the power should be divided into factor of alpha. We multiplied by P1. Let's say this one is 0.2. So 20% power at P2 and the rest, means the 80% power is at P3. So it's 1:4. So the division ratio is 1 to 4. So in the similar way, when incoming, let's say 2 different power, it can be different signal power or same signal with different power. Same signal means the same frequency with different power, or same power with different frequency, or different frequency with different power. What it will do, it will just simply add here and give us the P1. Means if regardless of the frequency, if it have 1 watt and if it have 1.5 watt, so we'll have around 2.5 watt here. However, there are some, for the resistive, there are some reflection. We already talked about it. We will know about it later on. And this is the basic 3-port network. I already have discussed a little bit in the previous lecture. And this is the how it converts. If in a basic scenario, like what we call it, the theoretically perfect scenario, ideal condition, supposed to be all the different ports, this port, and this port should be matched. If these all ports are matched, I already have many times mentioned that one, that matching is so important to get rid of the reflection. If theoretically matched, means there will be no S11, S22, and S33. It means they all are 0. So this happens to 0, and then if the network is reciprocal, then this become like this. And so this, we know it from the matching network theory. Sorry, network analysis, microwave network analysis. So I will not discuss these things more, but need to connect with this power divider and combiners. So here, let us consider now that we're going to design a lossless power divider. which is a transmission line model here. A transmission line model here is given. So where there are three branches. This is the input power. So input power have its own impedance, and there are two different output power junctions. Let's say I wanna input split into two different power ratios, but each of the transmission line have its own impedance, isn't it? And we have a junction here. Usually there should be a junction susceptance here, supposed to be that like that, and we consider there will be a voltage here. Okay, but let us make it more simplified and make it like a T, and then try to analyze what is there. So it's supposed to be like this. Okay, so P in will be there, and P1 and P2 will be out, and Z1 and Z2 is the corresponding output, different output ports line impedance or characteristics impedance, and the input impedance of the characteristic impedance of this line is input line is Z0. Now if you analyze this one, because these are mostly in parallel, so if you analyze this one, you need to find the admittance. Here you can find out that this parallel with this, isn't it? So this parallel with this plus the junction capacitance, junction susceptance here, right? But if it's a lossless, it's supposed to be the B should be 0. So it means the Y in is equal to 1 by Z1 and 1 by Z2, which is actually parallel to Z0. So we now know that here these two junctions are actually parallel with this input junction. Now we go deep more inside the analysis. Let us do an example, and by doing the example we will learn how to analyze the T junction power divider. This is example from the David Posner book. The example 7.1, the T junction power divider. It says a lossless junction power divider has a source impedance of 50 ohm. Source impedance means actually line impedance or characteristic impedance. They are the same thing. Find the output characteristics impedance so that the output powers are in 2:1 ratio. Compute the reflection coefficient seen looking into the output ports. Okay. So let us go. Let us remember this thing. This is 50 ohm, and the power output ratio is 2:1. So okay, here this is the design. I made it like a bit more realizable. So we have a Z0 is 50 ohm. So we have a P in, and then we're gonna separate the P in into 2 and into 1. So P1 is equal to 2 of P in, and P2 is equal to 1 of the third portion of the P in. So the P1 and P2 ratio is 2:1. But we also know that the total power combination of these two ports is coming from here, right? So theoretically, P in is equal to P1 plus P2. Now from these two equations, we find out what is in terms of P in. So in terms of P in, the P2 is 1/3 of the P in, and the P1 is 2/3 of the P in, means the input power. So this is what we have. This is what we have. We go back to what we have and compute the reflection coefficient, right? And find out the characteristics impedance. So our goal is to find out what is the characteristic impedance of Z1 and Z2. 2. Okay. Now let's try to analyze from here. This is just voltage analysis. Hmm. It's electrical one circuit 101 type of analysis, which is not so difficult. We know that power, input power, is half of the voltage multiplied by the impedance, isn't it? Since we know about this voltage here, this is V naught. I forgot to put it there actually, supposed to put it. But this is V naught, remember this one. This is V naught. So anything power delivering is actually this half of this square divided by Z naught. So here we have this one P in, right? So similarly, if this is the input power, so for this one, this should be same because the junction is, they're sharing the same junction, P1, P2, and P in. So V naught is common for all. So it is half V naught square by Z1, and for P2, it's half V naught square by Z2. Now, from here, we derive something. Now we're going to use this one to analysis more. So for P1, we know twice P in by 3, right? So twice by 2 by 3 P in, right? Now we know this is equal to this. So put it here. So this and this becomes equal, right? Now we see this goes away, this goes away, half goes away, half goes away. So Z naught stays and 2 by 3 stays, right? So Z1 becomes what? 3 Z naught by 2. We know Z naught. So we put here 50, we have 75. So the first is done. So we got Z naught. In similar way, we use this one here, 1 by 3 of P in, 1/3 of P in we using here because we derive here. So P2 is equal to this and this. So these two together equal. So half goes away, this goes away, and this equal to this stays. So Z2 becomes 3, Z1, which is 150 ohm. So the first portion, this portion is done. I hope this is not so difficult for you since we supposed to know this already. But well, study is of course important. In terms of this, go back to your electrical circuit analysis a little bit, then you can understand it much easier. So now we're gonna use these values, these two values, because these characters, all the characteristic impedance are known. So from all the characteristic impedances, we can actually find out the reflection coefficient of the, compute the reflection coefficient in looking into the output port, right? So all the output port we can find out the reflection coefficient of all the output ports.